In this segment we're going to be talking about what is maybe every IB student's favorite topic, measurements and uncertainties, and carrying uncertainties through our measurements. So we're going to really quickly just mention that we're using the metric system, and our normal measurements, our fundamental units, are meters, kilograms, seconds, amperes, kelvins, moles, and candelas. These are the units from which everything else is derived. These are the units when you calculate things, you need to have your measurements in these units. So, when calculating velocity, which is distance per unit time, we should be calculating with meters and seconds. When calculating force, which is mass times acceleration, we should be using kilograms, meters, and seconds. If you're not using these standard fundamental units, you are not doing it correctly. From these standard units, we get our derived units. The Newton, the joule, the volt, the ohm. There are a wide number of derived units that we get. And you can see here we have what the base units for those are, and you notice that in all of them it's what was on the previous slide: kilograms, meters, seconds, amps, all some combination of those fundamental units, and we've simplified them by giving it an equivalent unit. So that's really all we're doing, is we're making it easier on ourselves so we don't have to write out all of these base units. We're giving it an equivalent unit that we call a derived unit. Along with these units, we're going to see prefixes, and let's bring this. Along with our prefixes, on a daily basis, we will be using kilo, we will be using deci, we will be using centi, and milli. On a less regular basis, we'll be using mega and micro and nano, depending on what we happen to be talking about at that particular time. But you need to be familiar with all 12 of these particular prefixes. You should recognize them. You should recognize their symbols, which are over here. The primary ones in the middle here, kilo, deci, centi, milli, you use so much that hopefully you recognize those. But become comfortable with the rest. They will come up on a fairly regular basis. Okay, now that that's out of the way, we can talk about uncertainty and error. This is where things get exciting. There are two types of error. Random error, which is the typical error that we're going to experience. We're not measuring accurately. We don't calculate correctly. We don't carry over data from one table to another. These are things that affect individual data points. These are things that affect one measurement here, one measurement there. They don't carry through the entire experiment. Systemic, on the other hand, are ones that cause the same error on a number of data points through an entire system. So if you don't tear your electronic balance before making your mass measurements, it could be off by 1/10 of a gram, 5/10 of a gram. In that type of scenario, every single measurement that you make is going to be off by 5/10 of a gram because the measuring device is off. So understanding that difference, that our random error affects data points here and there. Systemic errors are ones that are inherent in the system. They occur repeatedly, and they affect a series of data points. Along with our measurement, we need to understand the terms precision and accuracy. The precision of a measurement is how close is it to your other measurements. Are all of your measurements similar in value for a specific trial? If the precision is high, the random error is low, and vice versa. If you have very low random error, you should find you have a very precise set of data. So that means all of the measurements are similar to each other. Accuracy is how close those measurements are to the actual accepted value, or how close they are to what should be. So you can have a very precise set of measurements that is completely inaccurate. The accuracy of measurements is generally affected by systemic errors. And so if you're measuring the acceleration due to gravity, for instance, and you take 10 measurements for a ball falling, and you calculate the acceleration due to gravity to be 15, 17, 18, in that range every single time, your measurements are all precise because they're all relatively close to each other, but they're completely inaccurate. So that's just an example of how that can happen. Now, with IB, we try and keep a relatively accurate number of significant figures, but as long as you're within 2, as far as IB is concerned, you're okay, but it's nice to know what they should be. When you're measuring, you should always obviously measure as precisely as you can with a specific device, but then we do what's called estimating the first uncertain digit. And so if you have a ruler, and we'll just draw this out real quick. Let's say we have a ruler and it's broken up into centimeters. And we're going to pretend here for a second that I'm really good at drawing centimeter spaces. And so we have 1 centimeter, 2 centimeters, 3, 4, 5, 6, 7, 8, 9, look at that, 10 centimeters in this ruler. And we have some object that we're measuring the length of. And so we lay this object on the ruler. It appears that this is a green bean. So we're measuring the length of a green bean from what I can tell. And so when we look at where it actually falls on the ruler, we start obviously at 0, and it falls roughly here. Now, as far as the ruler is concerned, that's 6, but it's obviously not 6. It's somewhere between 6 and 7, and if we call this right here about 6.5, it's slightly less than 6.5, we call it 6.3. So this is a much more precise measurement than just saying 6 or 7. It's much closer to the actual value, and we've added a significant figure here. Okay? Okay. And this idea of uncertainty it's simply related to the limits of our scales. If we have a meter stick, if we have a balance, they can only read so small, and so we can only get measurements that are so precise. Now with our uncertainty, and here's where our calculations are going to come in a second, we have 2 types of uncertainty. The first is what we call absolute uncertainty. And the absolute uncertainty is the specific value in the units that you're measuring of the uncertainty. So something like plus or minus 0.001 meters if we're measuring length or distance. The relative uncertainty is relative to that measurement and is expressed as a percent. So it's basically, we can think about it as the percent uncertainty is another way to look at it. if we're adding or subtracting in an equation when we're calculating, we're going to add or not subtract, we're just going to add the absolute uncertainties of the measurements. If we're multiplying or dividing, we're going to add the relative uncertainties. And so what this is going to look like, let's run an example here. So let's say we have, we're trying to find the net force. And to find that, we have two forces. We have F1 plus F2. And let's say that F1 equals 5 newtons. And our instrument that we're measuring with has an uncertainty of plus or minus 0.5 newtons. Okay? So that right there is our absolute uncertainty. Then F2 is, let's say it's going in the other direction, it's negative 10 newtons. And again, we use the same measuring device, so it's going to have the same uncertainty in the measurement. So we plug these into our equation, and we're going to get 5 newtons plus negative 10 newtons, which we know hopefully equals negative 10 newtons. But we then also have to add our uncertainties. So our uncertainties, we have 0.5 plus 0.5, so our total uncertainty is 1 newton, and so our final answer here is going to be negative, that's a big eraser, negative 10 newtons, negative 5 newtons is what it actually should be, and we're going to, so negative 5 newtons, plus or minus, we take this is our absolute uncertainty, put it there, plus or minus 1 full newton. So our answer, our net force in this case, is then negative 5 newtons plus or minus 1 newton. Now if we are multiplying or dividing, on the other hand, it's a little bit more complicated, only in that we have to find the relative uncertainties, the percents, basically. So if we use the equation V equals IR, just for a sample, this is voltage equals current times resistance. We're going to take a couple measurements. Let's say we have a current of 5 amps, and the uncertainty in the ammeter is plus or minus, let's see, we'll go with 0.1 meters. Or 0.1 amps rather. And the resistance is, we'll use 10 ohms here. And the resistor measurements have a tolerance of plus or minus 0.5 ohms. Okay. So now, the first thing we have to do is find the find the relative uncertainties. And so the percent uncertainty, and that's going to be this, the absolute AU, absolute uncertainty, over the actual value. And I'm just making these symbols up, they're not written down anywhere. Absolute uncertainty divided by actual value. And so here we have 0.1 over 5 amps. And so that's going to give us a value of 0.2. We're going to express it as a percent, so we multiply by 100, and we get 20%, 0.02, not 0.2, and so that's going to be a percent uncertainty of 2%. We're going to do the same thing for the second one. Here we have an absolute uncertainty of 0.5. We have an actual value of 10, which is going to give us a value of 0.05. We're going to convert that to a percent, which gives us an uncertainty of 5%. So now we're going to do our regular calculations, plug these into V equals IR. So 5 amps times 10 ohms gives us a potential difference of 50 volts. Don't worry about the units now. We'll talk about this equation later on in the year. Now, to get the uncertainty, we add our relative uncertainties, and we find that we get a total relative uncertainty of 7%. So this is plus or minus 7% if we're dealing with relative uncertainties. But if we're asked to find the absolute uncertainty, it's simply a matter of finding what percent of 50 is 7%. So we're going to multiply by 50 times 0.07, which is going to give us an absolute uncertainty of 3.5 volts. So we have, when it's all said and done, 50 volts plus or minus 3.5. Well, what does this actually mean? What this is telling us is that based on our calculations and our measurements, we've gotten a measurement or a value for the voltage here of 50 volts, but in reality that measurement could be anywhere between 46.5 volts and 53.5. We know with a pretty good amount of certainty it's between those 7 measurements. It's somewhere in that range. Then finally, to show uncertainty and error graphically, we use what are called we use error bars, and the error bars should be the same relative length to represent how much error there is. And then when we draw our lines of fit, when we calculate our lines of fit, all of those points in their error bars should fall on the lines of fit. If they don't, we consider that data point an outlier. And so let's look at what this looks like. So here we have error on both the x and y axis, and so you can see that our data points actually end up looking like plus signs, really, because you have the x error and the y error, and our line of fit passes through 1, 2, 3, 4, 5 of the data points, but this particular data point here does not fall on the lines. Since it doesn't fall on the lines, we consider that an outlier. And then in the slope, so we have error in our data points, we also have error in our slope. And here we find the maximum and minimum slopes by making slope lines that start at the top of the leftmost point and end at the bottom. And then our minimum, we start down here at the bottom of the error bar and cross through at the top down here. And so that gives us a range for our slopes. It gives us the maximum and minimum possible slopes for our data.